Alright, let's talk about ways to extend the cell matrix concept. So the cell matrix, as we normally talk about it, is a block that has inputs and outputs, like this. And there's some function inside here which maps inputs to outputs. And each output corresponds to some function. So for example, this is north, south, west, east. The function value coming out of the east is some combination of the north, south, west, and east inputs. And in the cell matrix, everything is digital, so this simply takes these four inputs and they're each a 0 or a 1. So based on the 16 possible combinations of inputs, there's 16 possible outputs, each also being a 0 or a 1. And this is typically represented with some sort of truth table. So here's your inputs, and here's your outputs. And we list all the possible combinations of inputs. And there's 16 of those, and for each of those we specify what the output values are. And the way the cell acts is when there's a certain set of input values, say 0, 0, 1, 0, it looks at these output values in the truth table and asserts those values to the four output lines on the north, south, west, and east. And so this function f, or these four functions f, north, south, west, and east, define the behavior of the cell, and we can represent it with a truth table. That's a very digital thing. And the universe, as we understand it, doesn't feel very digital. It feels more analog, more continuous. So an early attempt at extending this into the analog domain was to envision a set of analog components. For example, we might have a resistor and a capacitor and a transistor. And there's different ways we can weave these into the cell matrix fabric. But for example, we could have some kind of crossbar possibility where we can take any one of these outputs of one of these components and connect it to an input of another component, or maybe bring it across and connect it to here, and so on. So you have some sort of crossbar set up and you simply make connections like a programmable fuse map, for example. And now our truth table, the outputs here correspond to these different connection points. And by putting a 1 in one of these, you signify a connection. By putting a 0, you signify no connection. And now, based on the value of inputs, we can have certain outputs taking place. And there's other ways that you can do this, and this begins to look like a field programmable transistor array or a field programmable analog array instead of an FPGA, which is usually digital, a gate array. That's not bad to come up with for D-mode behavior, but when we start talking about C-mode behavior, where we have truth tables being taken out of one cell and copied into another cell, the question of how to take this information, encode it, and then transfer it through possibly some circuitry like this into another one, that's a process that's a little hard to define in a meaningful way, because these are still digital, they're still binary, but the stuff that's being processed by a circuit built out of this stuff is almost necessarily analog, and we can force it into a digital mode by clipping values and so on, but then we're kind of losing the real power we're after of being able to build things like oscillators and amplifiers and so on and so forth. So this attempt was dispensed with. That was arguably version 2 of the cell matrix, which brought us to cell matrix 3rd generation. So CM3G, which is also called SLP, or the Songline processor. And this was a different approach to implementing a continuous non-binary version of the cell matrix. So we'll talk about that in the next video.